plasma and fusion demonstrations. Part of a series of activities in plasma fusion physics to accompany the Contemporary Physics Education Project chart, Fusion, Physics of a Fundamental Energy Source. The physics of plasma globes. In this section, we will use a plasma globe to study some of the characteristics of plasmas and the nature of the energy they radiate. Comparing spectrum tubes with a plasma globe. In this activity, we will observe the characteristics of the spectra of known gases contained in spectrum tubes. We will then compare these known spectra with the spectra of unknown gases inside the plasma globe. Comparing a xenon tube with a plasma globe. Here on top is a xenon tube. On the bottom is a plasma globe. Creating a vertical streamer will allow us to use diffraction grating to view the plasma globe spectrum. Compare the xenon spectral lines on top and the plasma globe spectral lines on the bottom. Comparing a mercury tube with a plasma globe. Here, a mercury tube is on the top and the plasma globe is on the bottom. Again, generating a plasma globe vertical streamer and using a diffraction grating, we can compare the spectral lines of the mercury tube and the plasma globe. Comparing a krypton tube with a plasma globe. In this segment, note that the krypton tube is on the top and the plasma globe again on the bottom. Comparing an argon tube with a plasma globe. Observe the argon tube on top and the plasma globe vertical streamer on the bottom. Comparing a neon tube with a plasma globe. In this segment, we are comparing the neon tube and its spectra with that of the plasma globe streamer. Comparing two plasma globes. As evident in this comparison, not all plasma globes have the same appearance. They do not all contain the same mixture of gases, and consequently their spectra may vary. When comparing the spectra of the two globes, it can be noted that the bottom globe's lines are slightly broader, and although faint, a few additional lines can be seen. These distinctions may be even more observable in the lab with a good grating or spectrometer than they are on video. Comparing the spectra of various tubes. Comparing a mercury tube with a xenon tube. The following tube comparisons provide evidence that although two excited gases may appear to be the same to the unaided eye, when viewed through a grating or spectrometer, they may be distinguished and even identified by their spectra. Comparing a krypton tube with a xenon tube. In this comparison, note the strong blue, green, and yellow lines of krypton on top as compared to the xenon spectrum on the bottom. Comparing a mercury tube with a krypton tube. Observe that the two spectra have similarities. One obvious difference, however, is that the mercury on top has spectra in the violet region, and krypton's lines on the bottom are in the blue region. Comparing an argon tube with a neon tube. When comparing argon on top to neon on the bottom, notice the strong red, orange, and yellow spectral lines of the neon gas. Observing the field around a plasma globe using a fluorescent tube. A high-frequency, high-voltage source within the plasma globe strips electrons from gas atoms within the globe, creating a plasma. The electrons and ions move at the source frequency, and an electric field. This electric field can be used to excite the gas within the fluorescent tube, and when the bulb is close enough to the globe, the bulb is noticeably bright. Observing the field around a plasma globe using a neon tube. As with the fluorescent bulb, the gas within the neon tube can be excited by the electric field which is surrounding the plasma globe. Observing the field around a plasma globe using a black light. When the field excites the plasma in the tube, the emission from the tube can be seen to cause fluorescence in other materials. Note the brightening of the handkerchief behind the black light. Making quantitative observations of the field around a plasma globe using a meter. To complete some rough quantitative tests of the electric field, we will use a multimeter set for AC readings with a wire connected to the positive terminal. The other end of the wire will be the probe, but to avoid the effects of our body's conductivity, it is best to use a dowel rod as a handle. Near the surface of the plasma globe, the voltage reading is approximately 160 volts. When the probe is moved away from the plasma globe, the reading drops accordingly. Please note that because the electric field is a vector, the orientation of the probe does affect the readings and should remain consistent. Making quantitative observations of the field around a plasma globe using an oscilloscope. Plugging the probe into an oscilloscope instead of the multimeter allows us to visually see the relationship between electric field intensity and distance by measuring the height of the pattern. Using the oscilloscope, we can see the oscillatory nature of the field related to the source in the plasma globe. The source field frequency is approximately 25 kHz.